Hello, math students. Exponential growth and decay models. A function that models exponential growth / decay is given below. Its p of t is equal to p sub 0 times e raised to the rt. Now this r, if it's positive, it's called a growth rate, and if it's negative, we call it the decay rate. This p sub 0, it's said p naught. It stands for the population at time 0, so it's the initial population, or the initial amount of something. E, of course, is Euler's constant, the 2.7 approximately. T is some sort of unit of time. And then over here we have population as a function of time. At the start of the year 1990, a population of rabbits is 100. 2 years later, the population is 125 rabbits. Use the exponential growth model to do the following. Part A is find the population of rabbits as a function of time in years since the start of 1990. I'm going to make a little table here to keep track of the quantities. We have year, t, and then we have population as a function of t. So in the start of the year 1990, we're going to say that's when time is 0, and the population was 100 rabbits. 2 years later, at the start of the year 1992, or in other words, time 2, the population at this time was 125 rabbits. Let me move this out of the way a little bit, actually. We're going to begin with the population model, plug in these points to figure out what p naught is and what the r is. All right, so we know that 100 rabbits is what we get when the population is evaluated at time 0. So now I'm just going to take this equation right here and just plug in t equals 0 and leave everything else the same. So we get p naught times e to the r times 0. Well, r times 0 is 0 and e to the 0 is 1, so we get p sub 0. You can see why p sub 0 is our notation for p at time 0. P of 0 is going to be 100. My model now looks like the following. P of t is equal to the p naught we can replace with 100. Once you determine p naught is 100, that stays 100. E to the rt. Once we know what r is, that's also going to stay constant. To help determine r, we need to know an additional point of data. So at time 2, the population needs to be 125. So 125 rabbits will be the population at time 2, which will be 100 e to the, and t becomes 2, so this becomes 2r. And this becomes an equation that we have to solve for r. So I'll begin by dividing both sides by 100. 125 divided by 100 is 1.25, or we can do fractions. Let's go 5/4 equals e to the 2r. Now I'm going to convert this to log form. So we get 2r, which is the exponent, is equal to log base e, which is natural log of 5/4. And then r, therefore, is 1/2 of the natural log of 5/4. And so our model becomes population as a function of time is equal to the initial population, 100, times e to the rt. I'm going to replace r now with 1/2 natural log of 5/4, and then all of this is times t. And this becomes our model. This model can be rewritten, though, in a different way. I'm going to put this t, multiply it to the fraction, and write that as t halves instead. So another way to write our model is 100 e to the t halves times natural log of 5/4. Now I'm going to use a property of logarithms that allows me to take this coefficient and bring it up as a power on the argument. So this is 5/4 raised to the t halves. And now we can use a property that allows us to cancel e and natural log. Any base raised to the log base b of a will just become a. Well, if these b's are both e's, e to the natural log of a just becomes a again. So what's going to cancel here will be this e and this natural log, and we're going to get 100 times 5/4 to the t halves. And let's leave that as our final answer. It would have been just fine, though, if you had stopped here, because these two expressions are identical. Part B, use technology to find the population at the start of the year 2000. Okay, so in our table, at the start of the year 2000, we got to figure out what t that would be. In fact, let me bring this table down over here so I can make it a little bit bigger and show you what it is we're trying to find here with part B. So part B, at the start of the year 2000, the time is going to be 10, because that's 10 years after 1990, and we're looking for the population at that time. Let's see what question C says. Use technology to find when the population is expected to reach 500 rabbits. So that's when we're looking for t. We don't know the time, so we don't know the year, but we know the population will be 500 rabbits. We can do this by hand and then reach for a calculator to help with the answers, but I'm going to do this instead by simply graphing our model and using that graph to find these missing points. The first function I'm revealing here, and let me zoom out so we can see this better. Here is the model p of t is equal to 100, which is the p naught, times e to the t halves times natural log 5/4. After I simplified that, we got this second model, which I'll reveal right now, but you can see it's the same graph. And to answer our first question, we wanted to know what the population is when t is 10. So x equals 10, and then see where that vertical line intersects our population curve. So we're going to say about 305 rabbits. Answer to question B. The population at time 10 is approximately 305 rabbits. Part C, if we want to know the time when the population is 500 rabbits. So let's go to our graph and make a horizontal line, y equals 500, and then look for where that intersects the population curve, and you get this 14.215 is the t-coordinate. 14.425 years after the start of 1990. And this would be an answer for part C. Okay, now we're going to do an example where we have something that's decaying. The population is declining exponentially. We're going to see that the r will wind up being a negative number. Now, I should point out that this r, let's go ahead and decimalize this r just to show that it's going to be a positive number. 1/2 of natural log 5/4. In fact, the graph of natural log of x looks like this, and it crosses at 1, 0. So whenever the argument is more than 1, then the y-coordinate will be positive. And whenever the argument of the natural logarithm is less than 1, then the y will be negative. You can see that from the graph. So I already know that this is going to be a positive value here because 5/4 is more than 1. So we get about 0.1116, we'll say. Sometimes this is also referred to as it's the growth rate. You might recognize this formula here. This looks a lot like the PERT formula for financial models. So you can think of r as an interest rate that's compounded continuously. And in this case, t was measured in years. So this is an annual growth rate, and technically it's compounded continuously. One way to interpret that. But it is positive, and r will always be positive in this model when we have something that's growing. Now let's look at the next example. At 1 p.m., a patient is administered 20 grams of a drug. The half-life of the drug in the patient's system is 3 hours. Use the exponential decay model. So when it says exponential growth or exponential decay, those are key phrases that are telling us to use this model here. It's the same model, it's just that r will be positive or negative depending on whether we're talking about exponential growth or decay. Sometimes it's called the law of uninhibited growth because these exponential curves, they grow and grow and grow and grow forever without any restrictions, which isn't really realistic because every environment can only support so much of a population. All right, so we can begin again with a table like we did before. Let's let t be measured in hours after 1 p.m. And I'm going to use capital D as the amount of drug. So at time 0 means 1 p.m. So at 1 p.m., the amount of drug in the system was 20. Every 3 hours, the amount of drug cuts in half. And so we know right now that 3 hours later, this will be down to 10. And then 6 hours after 1 p.m., cut 10 in half. So every 3 hours, it just keeps cutting in half. You could continue this table this way, but we're only going to use the first 2 bits of data to create the actual model. Let's begin with the fact that we know that 20 grams is the amount of drug at time 0. And at time 0, we're going to get, I'm going to say d sub 0. So I'm using d's instead of p's. That's the only difference. D for drug. E to the rt, and t is 0. We plug 0 into the model. This becomes just a 1, so we just get d naught. So d naught is 20. So our model currently is d of t is equal to 20 times e to the rt. We need to find r next. And that's where we're going to use this second bit of data. So we know that there will be 10 grams at time 3. And we plug 3 into this model, and we get 20 e to the 3r. Now we just have to solve this for r. So divide both sides by 20. So we get 1/2 equals e to the 3r. Then we're going to convert this to log form. So we get the exponent 3r is log base e, which is natural log of 1/2. And then divide by 3. R is equal to 1/3 natural log of 1/2. If the argument of a logarithm is less than 1, then that logarithm will be negative. That's true for all logs whose bases are more than 1, I should say. So this is a negative number here, 1/3 times a negative number. You can also use this property of logarithms to rewrite this, which is commonly done. Remember that if we have log of a fraction, you could do log of the top minus log of the bottom. Or log of 1 is 0. So we could change natural log of 1/2 to just negative natural log of 2. Here's another property we could use. Change 1/2 to 2 to the minus 1, and then use property 8, where the negative 1 drops down. And so negative log 2 is the same thing as log 1/2. So another way of writing this is to say that this is negative 1/3 natural log of 2. 1/3 of natural log of 1/2. So about negative 0.231. And then if I were to try to do negative natural log of, let me just make this 2 inside here, you see we get the same thing. So our model is d of t is equal to 20 times e to the rt. And I'm going to use this r. I'm going to multiply that by t, which means be careful you don't multiply the 1/2 by t. You got to multiply the 1/3 by t. So this is raised to the t-thirds natural log of 1/2. And we're going to do something similar about how to simplify this. I'm going to use the property of logarithms that allows me to move that up as a power on that 1/2. So d of t is equal to 20 times e to the natural log of 1/2 raised to the t-thirds. And now we can cancel the e and the natural log. And that gives us d of t is equal to 20 times 1/2 to the t-thirds. And this we're going to use for part A. Now for part B, use technology to find the amount of drug in the patient's system at 4 p.m. So 4 p.m. is 3 hours after 1 p.m. So technically we already know the answer to that. Right, if I were to put one more column in here, put an actual time column in here. So time 0 is 1 p.m., 3 hours later is 4 p.m. So notice, because we knew the half-life was 3 hours, I really didn't need to do all this work here to answer question B. The data for it was already right here. Every 3 hours, the amount of drug cuts in half. So from 1 p.m. to 4 p.m., that's 3 hours. That means we expect the drug to go from 20 grams down to 10 grams. Now watch what happens when you plug in t equals 3 into this. And we're going to do this one actually by hand. So plug 3 in for the t. So that gives us a 3/3. 3/3 is 1. So we just get really 20 times a half, which gives us that 10 grams. There's the answer to part B, but we already knew that. And now for part C, use technology to find when the amount of drug is expected to be 4 grams. So now for part C, we're saying, okay, when this gets down to 4, at what t value is that? And then we got to figure out what time that is. So I'll use technology for this part. So here's 20 times 1/2 raised to the t-thirds. And we were interested in time 3. Here's that 0.3 comma 10 that we already knew about. But we're interested in determining the time at which there's going to be 4 grams in the system. So I'm going to do a horizontal line, y equals 4, and find out where that intersects. This model will get down to 4 grams when t is 6.966. If you want to round that to the nearest tenth, we would have 7, essentially. And this is 7 hours after 1 p.m., so the time would be around 8 p.m. This will answer part C. All right, so this one was an exponential decay model, and we had a negative growth rate, if you will. We call that a decay rate when r is negative. Okay, let's go to the next example. The model below is a consequence of Newton's law of cooling. Newton's law of cooling basically states that the rate at which the temperature of an object changes is proportional to the difference between that object's temperature and the surrounding temperature. So if you were to throw a very hot object into a cold environment, it would cool off more quickly because the gap between the two temperatures is larger. As the object approaches the temperature of the environment, then it cools off not as quickly. Same thing if you were to put a cold object into a hot environment, and that leads to a differential equation, which leads to this production of this model here. So all you have to do is know this model. Let's explain what these different symbols are. Capital A is the ambient temperature, and the word ambient means the surrounding temperature. So if you put a cold object into a hot oven, the temperature that's in the oven would be the ambient temperature. T naught is the initial temperature of the object. And we are also assuming that the ambient temperature is somehow maintained, because normally if you put a hot object into a cold environment, but you don't maintain the cold environment, then the two temperatures will approach each other. The hot object will warm up the cold environment. But if you can somehow maintain the cold environment, then the hot object will just continue to cool until it gets to that maintained cold environment. Same thing is true in the other direction. So we're going to assume the ambient temperature is maintained, and it's the temperature of the object that's in the environment that's going to be changing. R is always going to wind up being a negative number in this case. Over here, this is temperature as a function of time. So capital T is temperature, lower t is time. Okay, a pie at 350 degrees Fahrenheit. So I guess this pie just came out of the oven. It's placed in a cooler that's maintained at 40 degrees. But we are assuming that the 40 degrees is not changing. It's somehow maintained. So we only expect the temperature of the pie to drop. Now, after 20 minutes, the pie has a temperature of 250 degrees. Use Newton's law of cooling to do the following. And so when it says Newton's law of cooling, it just means use this model. This is very similar to what we did before. I'm going to do another table where we have time and temperature. And this is temperature of pie, not the surrounding temperature. So at time 0, the temperature of the pie was 350 degrees Fahrenheit. And then this said 20 minutes later. So we'll measure t in minutes. So 20 minutes later, the pie has cooled to 250. A and T naught are given to us, but we're going to have to figure out what R is. So we know that initially the temperature is 350 of the pie. So that's the temperature at time 0. Well, using this model, that's going to be A plus T naught minus A times e to the 0. E to the 0 is 1. Then the A's cancel. And so in the end, you get just T naught. The T naught is the 350. We already knew that, though. So we're going to just take that as a given. And also that the A is the ambient temperature. That's the 40 degrees. That's the temperature of the surrounding environment. So what I'm going to do is just skip this and go straight to plugging in A and T naught with the known values. So our model becomes temperature at time T is equal to the ambient temperature, which is 40, plus the initial temperature of the object, which is 350, minus the ambient temperature of 40, e to the RT, which I'm going to simplify what's in the parentheses there and write this as 40 plus 310 e to the RT. This is our model, and the only thing that we need to now find is R. That's we're going to use this second bit of data. So we know that 250 will be the temperature at time 20 minutes. So that's going to be 40 plus 310. Change the T to 20. So this is e to the 20R. And we want to solve this equation for R. I'll begin by subtracting 40 from both sides. So that gives me 210 is equal to 310 e to the 20R. Divide 310 both sides. So 21/31 is equal to e to the 20R. Natural log both sides. We get 20R is equal to natural log of 21/31. Therefore, R is equal to 1/20th natural log of 21/31. I told you up here that for these models, R should always turn out to be negative. And in this case, 21/31 is less than 1, so the natural log of it is negative. So it's about negative 0.0195. So we have our temperature model is 40 plus 310 e to the R times T. So I'm going to multiply this R by T, which means the T goes here with the 1/20th. So that's going to be T 20ths natural log of 21/31. The same simplifying. We're going to take that T 20ths and bring it up as a power, and then cancel the natural log and the E. So in the end, our model looks like this. Temperature at time T is equal to 40 plus 310 times 21/31 raised to the T 20ths. And we'll stop here and say this is my model for temperature. So that's part A. Now I'll use technology to find the temperature an hour after being placed in the cooler. Now, mind the difference in units. 1 hour is 60 minutes, and T has been measured in minutes. So we would want to plug in 60 and figure out temperature to answer part B. And part C is use technology to find when the temperature is expected to be 50 degrees. So we put 50 here and say, hey, when does that happen? So these are the two missing points we're looking for, and we'll use technology to do both of them. Okay, so here's the T function. If you click on this purple, you can see clearly we start at time 0, the temperature was 350. And since the cooler is maintained at 40 degrees, you expect the temperature of the pie to approach that 40 degrees. So you expect a horizontal asymptote here. So if I do y equals 40, this does make a horizontal line. If I zoom this way, you can see it's an asymptote. The reason that is because as t approaches infinity, this part of the equation will shrink to 0, leaving us just the 40. In other words, as t approaches infinity, the temperature approaches 40 degrees Fahrenheit. And that makes sense because you expect the temperature of the pie to get closer and closer to the temperature that's maintained inside the cooler. Now let's go ahead and answer questions B and C. Part B, we have at time 60, what's the temperature? So I'll do a vertical line at change x to 60, find that point and say at time 60, the temperature is expected to be about 136.4. And then for question C, what's the time where the temperature will be 50? If I had said 20 there, then you would have said never, because it cools down to 40 degrees and stays at 40. It will never get down to 20, but it can get down to 50. Do a horizontal line at height 50, so it's about 176.3 minutes, and that will be the answer to part C. Okay, and one more example. A logistic model is used for populations that are growing in an environment with a maximum capacity. Now this is actually a more realistic model because every environment can only sustain so much of a population. The law of uninhibited growth gives you an exponential curve that gets steeper and steeper and grows without bound. A logistic model is a model that looks exponential at the first, but there's some sort of max capacity that as you get closer to it, the population has to level off again. And you get a curve that looks like this following a horizontal asymptote, where that dotted line is the maximum carrying capacity of the environment. Suppose the population of owls in a sanctuary after T months is given by the function below. Use technology to do the tasks that follow. This time, the model is given to us entirely. There's no R's to discover, no P naughts to discover. So let's begin by just graphing this. Population at time T is equal to 300 over 1 plus 20 e to the negative 0.1 t. So you can see that shape we were just describing. And you can see exactly where it's leveling off. It looks like it's leveling off at a height 300. We have a horizontal asymptote at y equals 300. It is not a coincidence that that's also the numerator of this model. So find the maximum number of owls that can be sustained. Well, that's going to be given by this numerator. We looked at our graph and we noticed that as t gets larger, as time goes on, we saw that the population at time t approaches 300 owls. So that's our max. Find the number of owls after 6 months. Well, t is measured in months, so I can just plug in t equals 6. Population at time 6 months And I'm just going to do that with a vertical line at 6. So we expect our population at 6 months to be 25.05. I could have also asked here, what's the initial number of owls? Initially, the sanctuary had about 14 owls, according to this model. You would find the initial amount by just plugging in 0 for t. So this part right here will become 0. E to the 0 is 1. So you would do 300 divided by 1 plus 20. 300 divided by 21 gives us that number of owls. And then question C, though, is find the time when the population is expected to reach 250 owls. Let's do a horizontal line at 250. That looks like about 46 months. Okay, and there's how we can analyze a logistic model. And that wraps up our examples of exponential growth and decay models.